Problem A2. Stellar stability. A star in hydrostatic equilibrium has inward gravitational forces balanced by pressure gradients. Though the material in a star is not simply an ideal gas, in many cases its pressure, P, and density ρ, are simply related by P equals K ρ gamma, for constants K and gamma. Throughout this problem, assume the star is spherically symmetric, its mass is conserved, and relativistic effects can be neglected. Question A. A thin shell of the star at radius r0 has density ρ0 and thickness delta r, and experiences an inward, gravitational field of magnitude g0. Part 1. What is the pressure difference delta P0 across the shell in equilibrium? Part 2. Suppose the entire star expands uniformly by a factor 1 plus x, so that the shell now has radius, r equals r0 by 1 plus x. In terms of delta P0, x, and gamma, what is the new pressure difference across it? Part 3. By considering the forces on the shell, write an expression for second derivative of r with respect to t valid when x is small, in terms of g0, gamma, and x. For what values of gamma will the star be stable? Next, we consider some simple models of stars, where gamma can be computed. Question B. In a giant star, the pressure is P equals P gas plus P rad, where P gas is due to the gas, which obeys the ideal gas law, and P rad proportional to T power 4 is due to blackbody radiation. In the star's radiation zone, P rad is much larger than P gas, but the two have a constant ratio. In this case, what is the value of gamma? Question C. A white dwarf is composed of electrons and nuclei. The electrons provide the outward pressure, while the nuclei cancel the electron's charge, and are responsible for most of the mass density. Consider a region of a white dwarf where the number density of electrons is Ne. Part 1. The electrons obey the Heisenberg uncertainty principle, delta P on delta x more O equal to reduced Planck constant, where delta x is the spacing between them, and delta P is the typical momentum that quantum mechanics implies they must have. Find a rough estimate for delta P in terms of Ne and reduced Planck constant. Part 2. Using this result, find gamma for a white dwarf. Part 3. A white dwarf has total mass m, radius r, and a relatively uniform density of order ρ is order of m over r cube. The radius is related to the mass by r proportional to m power n, for a constant n. Find the value of n.